All right, what's up, everybody? Welcome back to Structure Free Learning. And in this video, we're going to talk about designing steel beams, probably like a first course or first introduction to designing or selecting wide flange beam sections in steel. And we're going to just kind of constrain things to compact shape. So basically spec F2 in the AISC 360 specifications. And we'll focus on a strength-based approach first, which means that we're going to try to satisfy the basic design relationships for steel in flexure, phi mn greater than or equal to mu and mn over omega greater than or equal to ma. And then we're going to check shear, and then we're also going to check some deflection limit states or service limit state. Now, the whole design process in theory could just be a guess and check. Like you could just guess a cross section and analyze it. But either way, it's important that you understand kind of the basic behavior. And so something you should know, or I'm assuming that's known before this video, is that you have an understanding between the nominal moment strength and the unbraced length of a compact steel section. This is really alluding to spec F2. If I were to visualize spec F2, this is the graph that hopefully you've seen before. And the cool thing about this graph is that it has basically all the failure modes associated with a compact wide flange shape. And it starts off with a fully plastic section when you have a low enough unbraced length. Yes! Now, I won't go into all the variables here, but this graph is useful because it really visualizes all the failure modes. And in particular, when the unbraced length is less than, let's say, a plastic slenderness ratio or a plastic length limit, then we have what's called the yielding of the cross section, which is really means that you have a fully plastic cross section. And when your unbraced length goes beyond this LP value, then all this failure mode here is called lateral torsional buckling. And just like compression buckling, elastic and inelastic version, LR represents this elastic limit, and this portion right here would be inelastic LTB, and then this portion on the right would be the elastic LTB. This moment at the elastic limit due to some residual stresses is 0.7 FYSX. And you might see it sometimes called MRLTB. All right, so that's pretty cool. The other thing that we have to be concerned about, or that maybe you're familiar with already, is the CB, which is the LTB modification factor, which accounts for non-uniform moment diagram. That number is usually greater than or equal to 1. It increases our moment, and so it allows us to have more capacity. And so this could be called this line that we initially drew is the basic strength. And if I take the basic strength and multiply it by CB, all these numbers are just going to go up. That point would be there. If I could multiply it by CB, and in fact, every point on this graph like this, and this would be the basic strength times C. But we can never go beyond that fully plastic, and so really this thing is capped. If this is something you're familiar with, we're in a good spot to learning and understanding the beam design process. And the beam design process is just my way of guiding someone who's learning how to design or taking a first course in steel design. Process here, I'm going to give you a flow chart, but the first thing that's going to be done is to determine the required strength, which is a structural analysis. And this usually involves lots of other things. There's usually a separate class for this, but this will involve loads, load combos, which you'll get from AISC 7. Then you'll have to do a structural analysis, which will involve some modeling. And hopefully from this, you'll be able to get like shear, moment, axial force diagrams. For us and beam design, this would be that required moment strength, or the required shear strength. And with ASD, you might use MAVA like this. And so once you have those, you're ready. You got some business. And so from there, really what's next is like, hey, what's the possible failure mode for my beam? And that is highly dependent on the unbraced length, which is really just alluding to that graph. And so hopefully there's enough understanding of the structure or whatever given information that you have to determine this unbrace length. If you know the failure mode, whether it's yielding, inelastic LTB, or elastic LTB, that alludes to an equation in the specifications. In fact, if I go back here, going back to here, in fact, this is spec. This MP equal to Fy, this plastic moment is equation F2-1 in spec F. And then this portion right here, this linear portion, is equation F2-2, and then this elastic LTB equation is equation F2-3. One simple case to start with is if the unbraced length were 0. So this is one possibility. Boom, LB equal to 0. That might have some language like continuous lateral support on the compression flange. And so there would be no unbraced length here. The other option is that the unbraced length is greater than 0. Let's start with this LB equal to 0, because when the unbraced length is 0, I can look at my graph here and I know that I'm here at unbraced length of 0. And that means I have my failure mode is going to be fully plastic. My nominal moment is going to be Fy times Zx. I'm using equation F2-1 from the specs. And so I can use the BDR to back calculate a required plastic section modulus. And once I have that, I can use some tools in the manual. I can select a trial shape with table 3-2, which is in the AISC manual. If my unbraced length is greater than 0, I say as a rule of thumb, maybe you start with the longest unbraced length. And if you have enough information, you're going to calculate CB. If you don't have enough information, you could just assume CB equals 1. It can turn out to be super conservative. This one is a little bit harder to figure out because our failure mode depends on the shape, and that shape has specific properties for these limits on whether the cross section is yielding, whether it's inelastic LTB or elastic LTB. I don't know where my unbraced length sits along the between LP and LR. I'm not sure where it's at. Thankfully, there's like this amazing table which is pages and pages long, but essentially it's the graph of this. It's this graph, the nominal moment versus the unbraced length for every hot rolled shape in the manual, and that is table 3-10. Now you're going to need some values here, but this will become a little bit clearer when I explain to you how to use table 3-10. Yes. All right, so now you've got trial shapes. Hopefully that satisfy the BDR for flexure. What we'll do next, you'll verify shear, i.e. you're going to check the BDRs for shear. So here then you're going to check deflections. And that's just saying that whatever max deflection that you calculate for your beam, that's going to be less than or equal to some limit that's established from AISC 7. So for instance, one criteria is that for the maximum live load deflection is equal to L over 360. So that's an overview of the whole process.